So along with being able to use molarity and volume to get into moles so that you can do stoichiometry, another very useful solution skill in solution chemistry unit is working on dilutions and how to calculate dilutions. So we talked about there being a difference between a concentrated and a dilute solution. So for example, here I have an example of a concentrated acid solution. Hydrochloric acid can be distributed right from the manufacturer in concentrated form, but the concentration is usually too high. There's too many moles of hydrochloric acid per liter for it to be useful to us in the lab or in pharmaceuticals. Hydrochloric acid commonly comes as a 12.0 molar solution, 12 molar HCl. And that means that each liter has 12.0 moles of hydrochloric acid molecules in it. That means it's very strong and very dangerous. It's about 12 times more concentrated than the acid in your stomach. Obviously, you can see how that would make it very dangerous. Most chemical suppliers will also have a selection of more dilute solutions. Where my concentrated acid was 12 molar, this solution is only 1 molar. And that's much more common for something that we might use in a lab. The issue is twofold. One, I am now paying to ship a lot of water because this is much less concentrated. It has much more water for the same amount of hydrochloric acid. And it's expensive to ship a solution like this. Also, most distributors will only have a certain selection of concentrations available. So if you need something that you can't get from a distributor, you need to know how to dilute it yourself, or if you need many different molarities of solution. So we're going to look at why and how we dilute concentrated solutions like concentrated acids into a given volume of a more dilute solution. And we'll be able to do that with any kind of solution to make any concentration that we need. So let's have a quick little thought check here. Why can't I just use 12 molar hydrochloric acid for every application? Well, and if you look at this, really all of these answers are correct. For example, if I only need a very small amount, it might be very difficult to measure it accurately. If all I have is 12 molar hydrochloric acid, what if I'm doing a small scale reaction and I only need 10 millimoles? Well, we know that molarity is millimoles over milliliter. So if I do some algebraic rearranging, millimoles over molarity is going to get me milliliters. 10 millimoles at 12.0 molar means I'm going to need less than 1 milliliter of hydrochloric acid if I use the concentrated solution. And it's pretty difficult to find something to measure very accurately at less than a milliliter that's not also pretty expensive or pretty fragile. So I could maybe use twice as much acid as I need. Now I need 1.6. Well, using too much acid might be impossible. We might not be able to neutralize it safely, or it might be if I put too much acid in, I get side reactions I didn't want. Also, anytime I have to use 12 molar hydrochloric acid, I'm using something that is dangerous. And if I can safely use a more dilute solution, it's going to require less in the way of personal protective equipment, or else, and it will be less likely that I could injure myself. So thinking about concentration, here's a question for you. Is the concentration of this orange solution, is the number of millimoles per milliliter the same all the way throughout the cylinder I see here in the picture? And absolutely it is. A solution is a homogeneous mixture. That means it's the same throughout the whole container. So now the next thing to think about is if I'm using millimoles per milliliter, is that going to be the same concentration as if I have a number in moles per liter? And again, absolutely it is. If there are 2 moles of solute in 1 liter of solution, then there's 0.002 moles in 0.001 liter. That's 2 millimoles in 1 milliliter. So the solution is 2.0 molar either way. Sometimes it's just a lot more useful to be able to do some numbers in milliliters because most of our graduated cylinders are graduated in milliliters. So let's say for a experiment, we want 2 liters of hydrochloric acid that is 0.0250 molar. But all I have in the stock room right now is 500 milliliters of a 1.0 molar solution. So now we want to think about how can I do this? So if we think about something that we've talked about before, millimoles is molarity times milliliters. So what I need is 2,000 milliliters at 0.0250 molar. That means I'm going to need 50 millimoles of hydrochloric acid in this solution. So now I have to think about where can I get this? Well, I've got a more concentrated solution. Well, how many millimoles of the more concentrated solution would I need? And it's going to have to be the same number of millimoles as what I needed for my dilute solution. When I dilute something, I'm putting water in. I'm not putting in any more hydrochloric acid. So if I need 50 millimoles, then I need to get 50 millimoles worth of my concentrated solution. And remember we said if molarity is millimoles over milliliters, then algebraically millimoles over molarity will get me milliliters. So now let's see how many milliliters I need to get that 50 millimoles. Well, 50 millimoles is what I need for my big graduated cylinder here. At 1.0 molar, that means I need 50 milliliters to get 50 millimoles. So I can use 50 milliliters of 1 molar, and that will get me enough millimoles of hydrochloric acid to make 2 liters of this dilute solution. So there's an old saying, people say, do as you oughta, pour acid into water. You never ever want to pour water into an acid because it is a very exothermic process. It means I hope you remember that it is going to get hot. In fact, if you pour water into acid, it will get so hot that it starts to boil the water, and now you have clouds of acidic steam, which is definitely not a great plan. So we would start with about 500 milliliters of water. We would add the acid and let that cool because water has a very high specific heat. If I have a larger amount of water, then it won't heat up as much. And then I would go ahead and fill it all the way to the 2-liter mark. So take this process and we can make it into a formula. Okay, and here's how I calculate it. Molarity times volume, ooh, that's millimoles. The millimoles I start with, M1V1, has to be equal to the millimoles in my dilute solution, M2V2. So my M is molarity. And one thing to note is that V2 is my total final volume. So if we look back at what we were doing before, we would use 2,000 milliliters because we wanted 2,000 milliliters of 0.0250 molar. And so hopefully you see that using this formula, you got the same answer as you did before. So let's practice a little bit here. There's a couple different ways we could ask one of these problems. Here's one. I have 500 milliliters of 6.0 molar solution, and I want to dilute that down to become a 1.0 molar solution. So whenever I see a dilution problem, I know I'm going to be using M1V1 equals M2V2 because the number of millimoles in my 500 milliliters of 6 molar is going to be the same as the number of millimoles in my more dilute solution. So I write it, I solve it, M1V1 over M2 gives me V2. And then I can go ahead and put my numbers in here. 6.0 molar, 500 milliliters. I want a final molarity of 1.0 molar. So I would actually be able to make 3,000 milliliters or 3 liters of solution out of just that 500 milliliters of 6 molar. So that's one way I could ask the question. Let's look at another way. So this, I'm going to use the same set of numbers, but now if you look carefully at what's on here, how much water do I need to add to the solution so that I get a 1 molar solution? Okay, so when I look at this part is all the same as it was on the slide before. M1V1 equals M2V2. So I write it, I solve it, I math it. 6.0 times 500 milliliters over 1 molar gets me 3,000 total milliliters. And so very often we'll see people write 3,000. But what's going to happen if I add 3,000 milliliters to 500 milliliters of 6 molar solution? The total volume is 3,000 milliliters, but 500 milliliters came from that 6.0 molar solution. So I have to think about how much water would I need to add. And hopefully you see you would need to add 2,500 milliliters of water because 2,500 plus the 500 initial gets me my 3,000 total milliliters of solution.